Okay, good morning. Today we'll continue to talk about transformers, and um, we are going to fill a source code that I wrote last year to actually see what the transformer works in practical. So let's continue to check what transformer is. After that, we understand what the transformer is. We'll do a short language model quick view or overview, a quick overview about what the language model is. If we have time, we'll talk about some modern or specific techniques that involved in modern language models, like positional encoding, ROP, which is a popular positional encoding method, and a mixture of experts. If we don't have enough time, that's okay, because next week we are going to discuss several popular language model architectures like Llama, JAMA, Mistral, or DeepSeek. So the reason that we're going from here, the transformers, to certain models specifically, is because a lot of people knows what the transformer is, but in order to actually use the transformers in modern large language models, there are certain variations and certain implementations considerations, implement considerations. So the best way to actually have the ability to understand modern language models is to look inside the components, the building blocks, and the techniques used in these modern models like Llama, JAMA, Mistral, or DeepSeek. Because although they are all sort of the transformer-based models, their implementation have certain different choice of like the nonlinearity, or like the how does it handle the key and the value. Like what we talk about the transformers, there will be key, value, and the queries. There are different ways to do that. So next week we'll talk about certain variation, popular variation, and details. There will be also some topics about the related to large language model, like the visual or the multimodal models. And also there will be things like linear replacement of attention, or like member or other linear transformers. We'll talk a lot. We will consider those kind of techniques as advanced techniques. So we will move those topics later, like linear transformers, like certain training method related to, say, the DeepSeek R1 method, like the GRPO or other method will be put a little bit later in this semester, because we will have to introduce the image generation method first, like diffusion method. But I'll consider like Llama, JAMA, Mistral, including a mixture of experts, as kind of the typical standard techniques in language model. So we'll introduce in these 2 weeks. Okay, so let's continue to check the transformers paper. Just remind that what we talked about last week, we talked about the architecture of the encoder. We talk about the architecture of the encoder. Okay. So certainly it is not happy when I draw something and sharing screen. Sharing screen seems to be fine, and drawing something seems to be fine, but they don't work well together. So I'm not using the drawing right here. Okay, I can still use it. So this is the encoder part. Also recall that in this encoder part, we'll have input embedding, which is just a lookup table for each token. Each token will translate it into a vector of certain dimension, and we'll add in some positional encoding, which we haven't talked into detail about it. We will talk about it later. There'll be attention right here, multi-head attention. We haven't discussed what the multi-head attention yet, but you already know what the attention is. The attention is simply we have suppose we have a query, key, and value. First, we do the inner product between the queries and the keys, and to form a weight for each keys. The key value are pairs. So for each key value pairs, and for a single query, we can find the weight for each key value pair related to this query. By using the inner product or dot product of the query and the key. And we talk about there is a scale vector, which is the square root of a dimension of the key. The reason is that by assuming the distribution is some kind of normal distribution, or at least there should be independent distribution. So we find out that the standard deviation is a multiple of the square root of a dimension k. So because Tamon normalization method is to divide by the standard deviation. So we divide it by the square root of dk to mimic the behavior of the standardization or normalization of this thing. Because the denominator here is a inner product. The inner product is going to be bigger and bigger when the dimension is larger. So we have to sort of cancel out the effect this value to be too big when dimension to be really big, because we typically have a dimension dk such as like 512 or 1024 or 2048, like 2k, 4k, or 8k, something similar to that. So that would be a really large things. We wish this architecture to scale well, so we'll have to do something to help us to be don't need to worry too much about the dimension, because if the dimension like a dk is changed, we will have to change the hyperparameter or like the architecture or a lot of different things. That is kind of against our purpose. We wish to scale these things up in a sense of like data, your sample, your data, I mean the data set, the size of data set, the size of the model, or the computation power, which we will talk about it in the scaling rule. So when the model size is getting bigger, the behavior of the things changes dramatically. That will hurt the things like the scalability. So we will wish to make it more behavior more consistent in different dimensions. That's kind of the motivation. But the reason that we actually divide it by square root of dk is that we have certain assumption. First is that we assume that the mean of each element is roughly 0. And we are kind of using the normalization, and they are independent. Then they are independent. And we're using the normalization method that divided by standard deviation. If we assume that the mean is roughly 0 and each component, kind of like a random distribution, they are independent. So this is the reason that we do these things. Okay, so this is the scale dot product attention. So by using it as a standard attention, we first will have like self attention. We have the QKV, but by using it as a self attention manner, we first. The reason that we call it a self attention is because we only have one input, but when we use a scale dot product attention, we need to have 3 different kind of input like Q, query, key, and value. So the way that we do it is we use a linear transformation, which it should call the like projection in this paper or certain other paper. We have some linear transformation to transform the single input into 3 different input. So we use a linear transformation to transform the input into queries and keys and the values. Because they are linear transformation, so we can actually assign the output of these Q keys and value to arbitrary dimensions. In fact, that is a typical use of linear transformation. Whenever we wish to kind of reshape our input into another dimension, we use linear transformation as a convenient tool or like a standard technique. Whenever the input is not exactly the shape that we need, and the reshape does not work well. 好，所以这边讲的是，只是说，当我们把之前讲的 scale dot product attention 用成，只要 scale dot product attention 就是长着之前像这个样子。好，前面的那个你有 query keys and values， 你这边做 inner product 得到，然后再做当然还要处理这 scale 刚才讲的那个东西，然后得到一组东西。然后呢 mask 我们没有讲，然后呢我们得到这个一组东西之后，经过 soft max 我们会得到它的 weight 嘛，然后把这个 v 做一个线性组合，就是做加权平均这边的 manipulation 就是在做这件事情，这是之前讲的 scale dot product attention 就这样子而已。但是我们要怎么把它当做一个叫做 self attention， 因为这边的重点是 self attention 啊。self 指的是我们 input 只有一种，就一组 input。那这个 input 要怎么把它变成3个东西呢？很简单，就是用 linear transformation。这是一个标准的技术。当我们想要把一组东西变成一个我们有一个元件嘛，它可能有一些特定规格的输入，那我们的目前给它的输入长得不一样，那标准的做法就是反正就用 linear transformation 把它转成我们要的样子。好，你要再加一个什么 nonlinear 也可以，但是比较少见。大部分如果是为了要把它改变它的模样，只是要改变它的形状，使用的方式，就是用那个 linear transformation 把它转过去。好，那我们继续再说明下去。Okay, so that is how the self attention works when applying to arbitrary attention architecture. You generally use linear transformation to transform your input into 3 different kind of meaning like query, key, value. There's something we haven't covered yet. Which one? One of them is the mask. We will talk about it in shortly later. But before that, let's talk about the multi-head attention. So what does it mean by multi-head attention? The multi-head attention is a combination of multiple of the attention blocks together. The motivation is that we probably need more than the attention. There are several different ways to interpret or to kind of explain what attention is. One interpretation is that attention is like we have a sequence of different elements, and this is our new element here. We wish to know which one is more related to this new element, this triangle element. So we will find the importance, like this one and this one is more related. If in a sentence like he kicks a ball, probably the most important related is if this is a triangle one. The most related thing is the kick, right? Because this ball is being kicked. So this is a verb and this is the target of this action. However, there might be several different kind of different attentions. Let's talk about it a little bit later. Let's first talk about this example, like the relation between balls and the kicks. So in general, when we apply the attention mechanism, she kicks A are all like keys and they have certain related values. So for each key, we use this we have a tensor. We have a vector for each of a token, and we use the linear transformation to transform this thing into queries. Into keys, key vectors, and this ball word also has this ball. Let's say it's a token. It also has a vector related when we use the linear transformation to transform into a query vector. So we use the inner product, the dot product from this ball to each of the key vectors, and we get these divided by the scale and make it pass through the softmax, and we get the weight of each one of the things. So the result says this is the importance or the how related of this new word, like a triangle word ball, to each of these different tokens. So that's the idea of one of the idea of the single head attention. We usually visualize that only one token is most related to this word because it is a softmax. Although it is soft, it is still max, right? Although it is soft, it is still max. So there will be one thing that we consider to be max in most of the case. Although there will still be some small values here and there, but there will be one max relation that is most likely related to this word. So that's one way to visualize the what or to explain what the attention is, at least in in popular science introduction to what a transformer is to general public. You can see a lot of images about similar to this one, like what is attention. You probably will see a lot of images. Let me sometimes you'll see like this key value query things, like or the things in paper, but a lot of time you will see something like this one, or this is related to this one. This is more related to this one, things like this graph, or like this one. The relation between one word to other word has the importance. Another way to view this relation is to view it as a yeah, oh yeah, different part. Another way to view attention is for people who a little bit familiar with the MLP. So it make an analogy of this attention to MLP. Because MLP is most likely just a linear transformation. Each layer of MLP is like a linear transformation, and we have applied a nonlinearity after a linear transformation. So you can see that the weighted sum of these values is kind of like a linear transformation. So some people will explain that attention is kind of like a linear layer, but it has a dynamic weight. So because the input of the attention is not a fixed, does not has a fixed length. So the weight of this linear transformation has to be dynamically determined. So the above measure here, the most measure right here, is to determine the weight on the fly and use a linear transformation on it. So it's kind of like a dynamic linear layer. It is not actually not wrong, and technically it is in fact correct, because a layer of MLP is just a linear layer. But I think the relation between linear layer in MLP and the attention is simply because they are all using a linear layer. And a linear matrix transformation, a linear transformation. It's just a coincidence that the linear transformation is used right here. But the motivation is kind of weak. I mean, the link between the MLP layer and I think it's sort of weak. It is most likely because linear transformation is one of the popular or kind of overly popular tools that we use here in the layer. So it just happened that here is a linear transformation. So it kind of looks like similar to the linear layer of what we use in MLT. But I would rather call it just a weighted sum or weighted mean, because a linear, a more intuitive or more like people can relate it to a terminology that people can relate it to is weighted sum or weighted mean. And it is used very often in our daily life. Like when we design a score, the grade of your semester, or when we have an interview of people, we usually have a different one category here and one category, like 30%, like a performance, like 20% maybe your paper testing's grade, and maybe like another 20% for your like a paper review or your resume, certain things like that. So we use the weighted sum or weighted average very, very often to solve things, like the most basic or most apparent way to get a single value of a score whenever we have multiple number as input source. 所以那个我会另外一种讲法就是讲，刚才除了那个什么字跟字的关联性之外，那很常见 attention 大家这样解释。另外一个就是 有人会解释说这是一个动态的 MLP，就是一般的那种 linear layer。但我觉得那个比较偏向就是它只是刚好都用到 linear 而已。哦，所以你当然要看成是一个动态的 linear layer 也可以啦。然后它也是可以看得做得通，因为它解释的问题就是因为你输入不一定长度嘛，所以你不可能有固定的 weight，所以我用那种动态方法决定它的 weight 啊，所以也可以这样看啊，有的时候也很方便。但是我觉得这个 linear 只是巧合，因为 linear 太常用了，linear 其实就只是一个加权平均而已啊，那加权平均太常用了，而且我们日常生活就非常常在不同的地方都是用加权的去做它，算是一种简化模型了。连我刚才讲的是那个什么给成绩那些东西了，但你做菜也是啊，做菜你会说什么东西最后加进去的话是那个多少比例的哦，多少东西的百分比的啊，应该说多少克的什么糖，多少克的盐，多少克的什么肉啊，什么东西，你全部混在一起嘛。当然，因为它加的顺序那些东西也很重要，但它第一个最重要的，因为看好几层嘛，最重要的一个东西其实就是它比例，然后再来才是给人的顺序啊，什么东西那是比较次要。但是你东西如果比例不对，那就完全不对了。所以我们会把东西简化的时候，会直接先看它的比例。你的营养成分也是啊，就是你看到那个食品标装盒上面营养成分也是，它就是上面放比例嘛。啊，你的那个东西什么东西比例多少，什么东西比例多少。虽然比如说它的脂肪和它蛋白质或什么中间还有很多细分，不是每个蛋白质都一样，不是每个碳水都一样。哦，糖有分什么果糖、葡萄糖那些的，可能的都不一样，但是它就是分成先用百分比把它放进去啊，因为同样的东西就算是它成分一模一样，它如果用不同形式放进去，你可能消化的时候吸收东西进去也不一样啊。但是最简单的一个做法就是用百分比啊，所以这个so the what I was explaining is just the weighted sum is a very convenient and simple way to simplify the things that get people to understand. So that's surprise that you can see that a linear layer used everywhere, including when we wish to change the dimension of our input. We use a linear, conveniently use a linear layer. So I didn't really buy that this one is a dynamic linear layer of like the MLP. But anyway, if the linear layer in MLP is something you are more familiar comparing to like the linear transformation in linear algebra, I can see that people are not too fond with the linear algebra. So suppose the linear layer is more practical or more like more more friendly tools to help to understand. So then why not? I'm just saying that there's another way to understand the linear layer of things because linear layer is just, I mean, linear transformation is not too scary. It's just a weighted sum. Okay. Anyway, um, this is this is the single head attention. But why do we need a multi-head attention? The reason is that sometimes you can imagine that in this, I got my stylus here. In this case, there's not only one relation, one type of relation. Although that okay, ball is a target that of this action, but also sometimes we also want to know who is acting on this ball. Who is acting on that is she is acting on this ball. And sometimes we want to know how many balls do we have. Also, maybe in this case, in this scenario, a ball is this A is more important to this ball. So we can imagine when we consider a sentence of text, there may be tons of different kind of relations. So maybe we, instead of just using one attention, we want to use many different attentions to kind of represent different different type of, we wish the model to learn different type of relations. Also, that's the why we need multi-head attention. Instead of just using one attention, we use multiple attentions. Okay, let me clean out this one. So that is just the motivation of why we need multiple different attentions. Because one sentence, there may be different kind of relations. Okay, so what is multi-head attention? Is simply we use multiple self-dot product attention together. So you can see that, okay, we have first set of linear mapping to map our VKQ to a different kind of things. Also, we get a first set of VKQ. You can call it a sub VKQ because we have multiple different head, and another set of VKQ, and another set of VKQ, another set of VKQ. Of course, if this is a self-attention, and because these VKQ are already can be considered as a linear projection from linear transformation from one single source, you can simplify this to be one single linear transformation and split them together to several parts that you need. We will discuss this in our implementation, our NumPy implementations. But the idea is we simply do the scale dot product attention multiple times. Like this one, but we do it multiple times. Because we want to do it multiple times, the only question is, okay, do this multiple times, do we need to share the values, or do we need to share the key, or do we need to share the queries? So that's the question. But we will kind of investigate these options. I mean, in this case, obviously, it seems like, okay, if we have multi-head, like we have 10 heads, we will have 10 set of totally different V value, key, and query. Okay, but do we actually need 10 different sets? Can we use one single value altogether? That is okay, because you can imagine that we just simply use different way to do the weighted sum to this value, but we use different kind of key query to do that. But it's still better to have different values to altogether, because they may represent different meanings. It all depends on what you do next here. But I think it is still kind of reasonable to make all these values over like 10 different heads. You can share the same value. That still work. What doesn't work is if your key and the query are all the same. Because if your key and the query are all the same, the weights, the dynamic weights you generated will be all the same. So that's totally against the purpose of using multi-head. So at least one of the things must be different. Either the queries should be different, or either the keys should be different. I mean, in these different over different heads. 我这边只是要说明一下，其实你这边有个选项，就你这边有一个明显的，不是这个选项不见得每个都合理，但是你可以看到，当我们要用我们说这个 multiple head attention 的时候，你其实要先看到选项。好，那最简单的当然就是我做了 multiple head，那我就是每一次用不同的 key query value 我现在如果是 10 head 的话，我用10组。但是你要看到这边可以看到选项，就是说我可不可以把这些 value 全部共用，或者我可不可以把 key 共用 query 共用，或全部都共用？那这边就有各种不同的组合嘛，2的3次方等于8种组合，哪个要共用，哪个不用？全部都共用当然不行了，因为结果都一样嘛。事实上 key query 你全部都共用的话，那它的 attention 的位置都一样，就有一点跟我们前面的 motivation 违背我们前面的 motivation。 所以至少 key 跟 query 两个东西，至少其中有一个要不一样。我是说，在这个10组之中，它有一个要是能够变化的。好，那value 我觉得 OK， 变不变都行。所以其实还有蛮多种组合，其实看起来是合理的。那能不能用就看你实际上训练的表现，或者是说后面这个东西它怎么组合的。比方说全部加在一起的话，这个东西就不适合都一样，因为加在一起它就分不出来，然后你变成等于只有一，但是它是 concate， 所以如果是 concate 的话，你的 value 都用一样的 value，其实有它可能它的意义在里面，特别是你后面还要做的是 linear。所以这边的话，你的 value 用不一样的，就是用一样或不一样，其实都有道理。但是他这边就是你要看到他这边选的就很单纯，就全部都用不一样。那 key 跟 query， 你甚至可以觉得 key 跟 query， 我的意思是说，同一组之间 key 跟 query 有必要用不一样，它用同一个，这也是一个选择了，因为它就是选择像不像嘛。那你需要变成 key 用一种 embedding，query 用一种，还是你通通用一种？这是可以讨论，或者是说可以选择的。但是首先就是说这边标准的选择就是标准的 attention， 这边的 self attention， 它是这边你要看到它的选择就是全部都不一样然后都用那个对啊，这边全部都每个都这边有9个东西你这边看到9个，但实际上应该如果说是10黑的话，有30组，它全部都是不一样。OK， so all I'm saying is that first you need to realize there are options. Some places that you don't have options, but some places you can have certain options. Even though it does not mention that you can have option, that you kind of need to aware that there's a possibility, potential options. So to help you to actually pinpoint the place, you need to notice the choice of this design. So of course, one choice is whether we use the single head or multi head, and the transformers here is using multi heads. There are some research and studies to try to use single head instead of using multi head, and I remember results says that well, this choice may not be as important as we may thought or as we may imagine. Because the thing, if we are trying to replace the multi-head attention to the single head, it seems like the result does not change too much. So it does not change significantly. So maybe this choice is not crucial. But anyway, as far as I know, most of the or maybe if not all of the modern popular models are using multi-head attention. Okay, another choice is here whether our key value and the query should be like different among different heads, or whether or not your key value, I mean key and the query, because they have the same dimensions. They must have the same dimension because you are using the dot product here, so they must have the same dimensions. Whether or not they have same like linear transformation, this is something that you can choose. But after you're aware that there is a potential, there are potential choices right here. You can notice that the choice in this paper is they're all different. Or these are all different scale attention, scale dot product attention here. And another choice, since we mentioned about that, another choice is instead of you using like a dot product as a way to determine attention, you can use another method, and you can also replace softmax if you really want to. Use other way to determine the weight. There are choice, and that is probably one of the key difference between like certain of the linear variations of the attention, because attention itself is quadratic. You need to do the quadratic means the power of 2 because if you have n keys and n queries, then you will have n square of like the inner product things, kind of like that. Okay, but so the complexity goes up to like quadratic. Okay, anyway, after we get like multiple results of the attention, what should we do with this output? Our goal is to still have one output that to have the same input dimension, same dimension as the input. This is because we will have to like stack several of these blocks together. So by the sake of scalabilities, we wish to every input and output have the same dimension. So that's our design choice. So since we have already have different outputs, so what should we do to actually get it into the shape? Get into the shape we wish we want it to have. We use linear. Again, we use linear, like we say. When we get something that is not or potentially not the inner shape that we wish we are expecting, we use linear to the standard way to is to use a linear transformation to transform it into another thing. So we use a linear right here. But we have multiple output. We still have some way to kind of aggregate or kind of to put them, collect all this data together. So every piece of information can contribute to the output. There are several different choices, like you can submention them together. That's one way to do that. But the typical choice is to use concate right here. There are other choices. There will be other choices. But here they use concate to concate them together. And I think there's nothing wrong to use concate. But anyway, because this is fixed length, we're calling it multi-head. Simply because we are using more than one head, but the number of heads is fixed. So we can easily concate them together to get a vector that we know the dimension is. No matter what is the length of a sequence, we get one single. Typically, every head is equal, so they output the same dimension of things of a vector. So we simply concate them together. So we can actually get something predictable length. And so we can use simply use a linear layer to transform this output to arbitrary shape that we want. Also, that's why here we'll have a concate and a linear together. Okay, so the only things that we haven't discussed yet is the mask. The mask is the difference between the encoder and the decoder. The crucial difference between the encoder and decoder. Okay, here, when we consider about the encoder, we are consider an input. Suppose the input has a length like 100 tokens. Then we transform it into a sequence of 100 vectors, right? And then we go to this block. So for each of the block, it is going to get exactly the same length because the input and the output has the same dimension. So the input here, suppose our embedding is like 1K, like for each token we get 1K 1K dimensional vector. So we have 100 vector, and each vector is 1024 dimensional vector. So totally we have 100 and times 1K numbers. suppose like that in our data. Suppose our batch size is just 1. The input and the output should be exactly the same. So no matter what we can consider this as a black box, although we already know what it is. But by consider it as a black box, because the details does not matter, we can already know that the dimension of the input and the output are exactly the same. And we simply do this attention, like multi-head attention and like MLP after the multi-head attention n times because of this. The mask here can be ignored because they are not using mask in the encoder. So the things that you need to aware is that it is not doing auto-regressive things like we discussed in auto-regressive. It's just simply kind of like the MLP. The input is we're doing attention, but for each tokens and each operation of the attention, they are related to every other tokens, no matter it is before this token or it is after this token. So for each time, they find a different weight using the we call it attention map. It controls attention map, which is you can consider is a dynamic weight that we talk about, and to compute the weighted average and of the vector, and then each vector is output from this MLP separately. So this MLP is applied on each vector individually. 好，所以基本上这边的话就是全面做个 multi-head attention 嘛，你进来的这个100个，你的长度是100的 sequence， 然后这100个 sequence 每个都是长度是1000的 vector， 所以进来跟出去是一样的。好，然后所以这边都so the shape we have a sequence of length 100 here, and the output is exactly the same. A length a sequence of vector. The length of the sequence is 100, and the dimension of the vector is 1024. So each part is the same, and output is the same. But here, the MLP is applying on each of the element of the sequence. Each element is a vector, but this MLP apply on this 1K vector, one by one, or like you can do it parallelly. What I mean is they are doing this individually. So there's nothing about nothing similar to autoregressive model. The mask can use to do different things, but the more the most obvious or apparent usage here, or the use that we are applying right here, is to use it to mimic the behavior of autoregressive model, because that is exactly what the decoder wish to do. 好，所以 mask 是要做什么的 ？mask 是用来模拟，或者是说让它来达到 autoregressive model 的功能。所以这边的东西就会加上 mask， 因为我们 so the multi-head attention or the actually the self attention part here is going to have a mask, so that we can mimic or like train the model in so that it can apply to the actual data as autoregressive model. So what does the mask do? You see that when we apply it as do the training, when we do the training, we still got 100 a sequence with the length 100。好，所以我们当我们在训练的时候，我们一定先丢进去，可能还是丢一个长度是100的 的句子进去。But what we wish to do is we wish to actually use the first token to predict the second one, then use the first two tokens to predict the third one, to use the first three tokens to predict the fourth one. So in general, we wish to use the first n tokens to predict the n plus one's token. So that's the idea. So in this case, when we because we have already fed 100 tokens in the model, so in principle, if we are not using any mask, the token which we are trying to predict, like when we try to predict like the 14 five tokens, we wish it to only see the previous 44 tokens. Let's just say 40 and 41. When we wish to predict the 41's token, we wish it to least one to only see all the tokens before it, that is the first 40 tokens. But if we're not using the attention module directly, it is going to see the future tokens, which is something we don't wish it to happen. So we're using a mask right here. The mask only, what the mask doing is, okay, when we try to construct the attention map, okay, we already got the attention map right here. That's for sure. But we simply ignore all the weights or making all the weights after the like the future tokens, like the tokens after the 41, like 42, the 42s, 40 seconds, 43rd, 44th, 45th, all the later tokens, we wish their importance to be 0. So how do we do that? We can put a max after a softmax, but that would be maybe too late because softmax is computed consider all the tokens together. So the way we do that is to make sure the future tokens does not kind of like they are not exist when we're doing the softmax. They have 0 weight. The output should be 0 and they should not affect any of the other things. Okay, so the math is going to make the things that is not in the past or the things in the future to become 0. But because the softmax using exponential, so in fact, we are going to make the output over here that is not in the max to become negative infinity. So exponential to the negative infinity, it is going to be 0. Also, that's what is actually in the implementation. You can see that in the NumPy code, how we actually implement it. 所以 mask 的作用就是放在这边，它的作用就是让在我们训练的时候，比如说我们要训练第40个要 output 的第41个 token 嘛，那它后面的东西不能看到，第41个不能看到，他看到第41个就结束了嘛，因为我们 output 第41个，这样就训练的时候它就失去意义了，所以它41、42、43它全部都不能看到。那怎么做到嘞？就让它不要在 softmax 里做任何影响。如果你要放在 softmax 后面，你说好，我先把 softmax 把它全部算出来，把后面变0，那这样不行的原因是因为前面我们需要全部相加等于1嘛。你如果先经过 softmax， 它就已经产生作用，那前面都会被影响到，所以你要在 softmax 前面就把它处理掉。那怎么处理呢？你不能直接把它变0啊，因为我们前面 softmax 有是 exponential 那个东西嘛，你可以 exponential 之后变0，但是它就通常 softmax exponential 在 softmax 会做的啦。好，那你可以切开来说是先 exponential 然后变0，当然也可以啦。但是因为 softmax 看成是一个东西，所以逻辑上来说，它这些 mask 就是把未来的那些41、42、43、44那些所有 token，你反正照样去算出那些 weight 也没关系。 但你算出来 weight 之后，你把这些 weight 全部换成是负无穷大，那负无穷大你经过 softmax，因为它是 exponential 负无穷大，它就变0了，那就真的就不会做任何作用。当然，你逻辑上来说，你也可以说，我不要用任何 mask，我就是直接绕回圈啊，干什么的，也是可以的。好，就是看实作了。但这边的作用完全所谓的作用，就是把它过滤掉，让未来的 token 不要产生任何 weight。Okay, so that's what the mask do. There's also a cross multi-head attention right here. So you can see that it is not a self-attention, but it is a cross-attention. In here, as we describe what the self-attention is, we only have one input. So each input is like a vector. For each token, it is a vector. Of course, the length of the sequence, we are assuming it to be 100. But we apply the linear transformation on this this vector of dimensional 1k and make it to be 3 different vectors, like a key, query, and the value. So that's how it does right here. But in here, it is a cross attention. It is a cross attention. So we still need to have some certain like the key, query, and the value. And so we have a query right here and a key value to be related to the results of the output of the encoder. Like we said, the output of encoder still have the same dimension as input. So you can view that the input from the encoder as a prefix sentence, as we already know. You feel free to actually refer to them as well. But they are considered to be a separate sequence. And you already know the whole sequence. And here is another sequence. You are only allowed to know what is actually already given to you. You already know. You can only know the tokens that before the tokens that you are currently working on. Okay, so this is just simply cross attention here, and we get an output. For each query, we get an output. Recall that the length of the output is the same as the length of the query. So the query must come from here. Otherwise, they will have a different length. Right? Okay. Also, the value the output dimension, the output of each the dimension of each output vector is follow from the value. So you also need to modify the dimension of this value to be the expected one. Okay, so that's what the decoder is. After we get output, we need to actually get one probability. For encoder, we can simply encode in some sequence. But for the decoder, we are wishing to have an output probability to output the next token. So I'm using a softmax and the linear here to get the output probability. For the GPT-like models, it is an output only. I mean decoder only model. So it doesn't have any encoder. So there is no multi-head cross attention at all. So the only difference between the decoder and the encoder is okay. First, they will have like a linear and a softmax to get the probability. But the key difference is here. Here we have a mask when training. In the multi-head attention, self-attention, we have a mask. And here, for encoder, it doesn't have a mask. Other than that, the architecture are pretty much the same. Okay, so, but As beside the architecture, they are also training in a different way. Obviously, because for autoregressive model, it has to be trained like an autoregressive way. But for encoder, there will be different way to do the training, which we probably will talk a little bit later in today's lecture. We hope so. We're getting a brief discussion overview about what it is, although it is not too related to the generative models, but it is for the completeness of this topic, we will have a quick overview of what the training of the like a BERT-like models can do. Okay, so this is pretty much the GPT. I mean the transformers model is the GPT is in fact simply using the decoder only, since with some modifications. The only one thing that we haven't talked about is the positional encoding. Okay, so let's search for the positional. Okay, we already find it. This is the positional encoding. There are different, like we say that there are different ways to do the positional encoding. Models are mostly chose to, I mean, for this transformer or GPT, they are chose to simply do an addition, a factor addition of the positional embedding to the like a token embedding directly. They do it. But how do we decide what the positional encoding is? One thing you can do, one popular way you can do is to do embedding like a lookup table, and you can train it. But the drawback is that it is difficult to actually, I mean, extend it to a longer sequence. There's no way to do that. So another way to do that is to use it's called the sine cosine encoding. Like they simply predefine the vector by using sine cosine function. So that is how the positional encoding is done right here. So in principle, it is possible, theoretically, it's possible to actually kind of do some interpolations to the things, to the tokens. I mean, if it is only trained on like a sequence of like 100, like the length of 100, you probably can extend it to another sine cosine cycle to increase it to 200, length of 200. That's one possible way to do that. Another way to do that is to consider more refinement, to have a refinement of the sine cosine things, but they all have certain drawback. So there are more modern way to do the position, but I think the things you can remember is that okay, the positional encoding can be randomly initialized and trained among the training passes. It could be learnable parameters, and it could be something predetermined, like using sine cosine function. But there are many different considerations, like can we extend the context? Can we do different things like just for example, when we try to extend the model to have a image input, can we make a two-dimensional encoding it? So there are certain considerations, but one popular way is to use in a sine cosine positional encoding. You can see this still in a lot of different code base like diffuse, not diffuse, transformers, or like other language model, and they can be trainable parameters. There are different ways to do that, and there's another potential choice to actually concate the positional encoding to the token embedding. But the popular choice is to add them together, and it seems to be pretty much fine to just sum them together. It is faster and no significant drawback in performance. Okay, so that's all about the transformer architecture. Let's go to the code to actually implement these things. You can find the code in here. This is the code I wrote last year for like deep learning language models. They probably you can still find the video streaming and maybe another recording about these things that I wrote this like you can see I wrote this on the fly. The purpose of this video is to demonstrate that it is in fact a simple architecture. The GPT is in fact a simple architecture that you can really understand. Do not afraid to fully understand the architecture of GPT-2。所以 GPT-2 绝对是一个你可以从头到尾完全了解的一个架构。然后从这个架构，from this architecture you can as a start point to understand more popular, more modern models to compare the differences between GPT-2 and other models. You can see, okay, what's the improvement and what's the difference, what other variants and what other choice, potential choice or the extra choice they made. But do not, I think it's more like the mindset things. If you consider already give up that, okay, every modern model are black box, I cannot understand, then you probably already give up about it. But in fact, it is surprisingly simple to actually fully understand everything about GPT-2. Also, you can see that I can actually write it on the fly. Although it is kind of a replay of what I actually do. The actual thing is that I write it in 1 or 2 hours, just on the fly, and just test it. But this recording is the second time I write the same code. So although there are several different choice in the programming perspective, I chose different way to write the program. But I actually have a reference that I already made like 1 day before the recording. So it is not exactly the like the ad lib or totally unprepared sense, because there are certain details you need to be sure to make everything correct. There are certain details. But in fact, if I don't have to explain every detail, I can write this code pretty fast, even though I have to do some certain debug, kind of boring. I actually spend less time than what you can see in the recording to write the code. But anyway, you can check this to get a feeling of it is actually achievable and doable to write everything from scratch. Okay, so but today I'm not going to write the code again. Because if I'm going to write it, it is kind of like the 5th time I'm rewriting this code. I'm going to explain what the code is, so you can understand the detail of the implementation of what the GPT-2 is. Basically, it is follow very closely to the architecture of the transformer that we have already talked about. I'm implement it using NumPy. So you can see that there's absolutely no magic or no, mostly no magic. You see I'm still using some library, but everything that discussed in the transformers are kind of transparent here. I'm only using NumPy. So if you know what NumPy does, like the matrix multiplication things, that's it. We are reduce everything to matrix multiplication. I'm not using like PyTorch or like using transformers or other things. I'm reduce it to simply like mathematical formulas that you can relate everything you see on the paper and in the code. But in order to, I'm actually using the actual GPT-2 weight, so you can load the GPT-2 weight in this code. As a history remark, GPT-2 is kind of open. It's open source, so they provide the source code in their own implementation. Although it kind of in the old code styles, like old framework, as I remember, but they are open source and they are open weighted. They are all weight. You can actually get the GPT-2 weight, but after GPT-3, they are not release any code and the weights. But I'm using the public release the GPT-2 code, and I'm using the safe tensor format instead the original format. I forget. So in order, but anyway, this is the GPT-2 format. And by the way, I also introduced how you can load the safe tensor format in this code. But anyway, the one thing that I'm not implementing right here is the tokenizer. I'm using tick token to get the tokenize. So this is kind of cheating, because if I want to do everything from the scratch, then probably I should actually write my own tokenizer. But instead, I'm using a tick token because there are certain details like you need to consider differences between the regular expression implementation in different libraries. So there are too many details. So even if I want to implement the tokenizer directly, I still have to use a regular expression library. And I probably should, if I want to follow the implementation truthfully, follow the implementation 100%, I cannot use the standard regular expression in Python. I have to install another module that is doing the regular expression. So I figure that kind of define the purpose. So probably I can. So in this code, I'm focusing on two things. One is in the transformer algorithm, and the other is on the how to do you actually load the safe tensor, because safe tensor is the most popular format. You don't have to worry about too much about it. It is simple, very simple serialization format. So I'm focusing on that. I'm not focusing on the tokenization. So yeah, so I'm using a tick token to do a tokenization. But anyway, you can see that you can find a public available weights of the GPT-2 models like GPT-2, GPT-2 medium, large, and XL models, which is the most capable model for GPT-2, that is GPT-2 XL, in safe tensor format. And you can get them from Hugging Face. I already give you a command like here that you can to retrieve these models by using command line, using cur command line tool. Okay, here is a translation table from safe tensor data type to NumPy data type. We'll only consider like a 1432, I32, I62, and U8, which is corresponding to this NumPy data type. And for each weight, because in this implementation, this is a kind of an object or like a class that I define it using name tuple. which is a Python kind of data type constructor, which is a common correlation data type in Python that I can, or like customizable data type. So you can if you wish to use like a class to define object, you can also do that. But anyway, this means that this is a class which has two component or like a property, like a W and B, which is similar to the weight and bias in like a linear layers. Okay, so I use this as a data type to enhancing the readability and to do more abstraction in the following. And I also get a get array things here to read things from the a list of string. I also give the data type hint right here, so you can see this is actually read things from a data buffer. That is, when I try to read things from the safe tensor, I can read them conveniently and get a NumPy array directly and reshape it into the desired shape. Because the from buffer only return a one-dimensional, like a flat array. So I have to reshape it into a desired shape. So these are one of the utility data type that I define, and this is a utility function that I define. It only have like 2 or 3 lines. It's quite simple. You can actually read it. First, I translate to get the desired data type here, and I get the begin and the end to actually just extract the begin and end from data offset. It is a tuple. You can see that is actually is a list of 2 items. So I actually get the begin and end. You don't actually need this, but I mean, there are other ways to do that. But I do this explicitly to extract the data offset to convert it. So there are 2 slightly very light way to get things that in our format. The only thing that I do here is using the from buffer, the convenient tool for NumPy, from buffer to get the byte buffer because I already read the safe tensor, the byte buffer. I get them here, the raw binary data here, and convert to read them to convert to a NumPy array by using this data type. This, like I said, it is a flat array. I simply reshape to something that we know that the shape should be. Okay, so here is a thing called the read weight. This is a total thing to actually handle to read things from the safe tensor. The safe tensor, like other format, it should have a head. Like most data format is kind of like it has a prefix to actually to help you to identify the file format of it. So you can skip them if you don't want to check them. Then it will have some kind of a header to contain certain information, like the how many different shapes it have. Because we'll consider safe tensor is just a collection of like NumPy arrays in different dimension. So it must contain some information about dimension, about the position of which it's going to be stored in the file, and it will also have a name so that you can easily apply it to like different actually apply correctly on your model when you load this array. So you can see that it can find the metadata, and for each different array it can find the name. It's just a small like first it read the header. The first thing is like a header things, like okay, how large is the header? The header is in fact in a JSON format, so I simply load them using JSON.load. It is standard Python library, and after I get a header, I retrieve the uh, I retrieve the weights one by one according to this header. So that's it. So every time I read things, I read the weights and get them. And because of I know the name of it, I built a dictionary. So for each name of the weight, I get the weight and bias, combine them together. So that read weight. Okay, so because that is not the point. Our point is to understand how the transformer algorithm is going to be implemented. So I'm not going to discuss the detail, but just so you know that this is a full functional way to read the self tensor. It is readable. So even though if it has some corruption on certain part of the things, it is very doable for you to investigate which part is remain in the data file. Even so, like if you download it, it is truncated. You only got like a 90% of the file. It is still okay because you still got the 90% of the data, and you can probably get a good use of this 90% of the data. So that's the main message I wish to deliver. Okay, next we are going to find the actual implementations. So first of all, we have to define the layer normalization, as you can find in here. Add and norm. This is a layer normalization. Like I said, normalization is a standard technique building block for modern models. Although, like we probably mentioned last week, the recent paper shows that okay, we can replace this norm by dynamic hyperbolic tangent nonlinearity, so make it easier to train or get comparable and roughly the same performance. But you can see that in here we use a normalization layer, and although there are different choices like group normalization or other normalization, but in GPT-2 they use layer normalization. Okay, let me go back to here. So here is the implement of a layer normalization. Okay, so let me, I have two choices right here. I can skip all these things, just mention, skip the details of things and go to still start from the whole implementation first. Or I can explain the building blocks of each thing separately, and finally, I mean, I can do it bottom up or top down manner. I have a choice. Because I have already give you an overview of the transformer architecture, so you probably already have an idea of what it should look like. So I'm going to give you a bottom-up approach to discard the code, which is more similar to the order of the code, because you have to define sub modules first, then define the main module. So I'm going to introduce in this way. But this is a tough choice because sometimes the top-down method is more intuitive. So just so if you feel that because the bottom-up method is a little bit boring, you haven't get anything yet, and you just go to all the details. But anyway, I'm trying to do that, and just bear with me to actually see the detailed implementation of each component. So first, layer normalization. And also, each of them has its own interest because each of them are very popular building blocks. Okay, for the layer normalization, I'm using this method to kind of mimic what the PyTorch does. So I have an initialization to initialize the weight and a call function, which is kind of like a forward. The forward in PyTorch is kind of enhanced version of the call because it can hook something, hook something like wrappers and things, do the pre-processing or like post-processing. So it can be considered as a multifunction or like a more like a enhanced version of a call. But basically, forward is if you discard, neglect those like pre-hook or post-hook things, it is pretty much like equivalent to the call function of the Python built-in metric method. So this one is like a forward. So what does it do? Our weights. First, I got the W and the B from the weights because our weights is like I mentioned before, it is a name tuple. A name tuple can be viewed as a tuple sometimes. So I'm using the properties of behavior of a tuple to extract the W and the B without specifying the name. If you are using a class, you don't have this benefit. You have to like self.weight.w and self.weight.b. But for the convenience, because this code is for explanation, so I'm getting this W and B kind of like the mathematical formula. And this epsilon is technical because when we define something by when I try to compute a fraction, we don't want the denominator to be 0. So we have to consider about that. So we always had some epsilon to at least make the code still working in certain corner case. So here epsilon, we define epsilon here. The default epsilon is like 10 power to negative 5, like 0.0000001. So it's a small number. And most of the time, you don't need to worry too much about it because it is set in by default. So the formula is simply a normalization formula. And first, x is the input. So x minus x min, which is remove the bias here. We use NumPy formulas like the keep dimension true to make them to be subtractable correctly broadcasting, to make the broadcasting correctly so they can subtract to each other. And we define by the square root of the variance. So this is kind of like a STD. But we use the x variance because we need to add some epsilon right here before we go into the square root. Instead, we can do the NP-STD and maybe plus the epsilon. But the choice here to be more like I'm going to mimic the PyTorch implementation. So this is the things that probably implement in the PyTorch and mimic the behavior. There are other options, but this one has certain numerical stability advantage. Because not only we are trying to avoid division by 0 or division by negative things situation, we also kind of solving the potential issue of the square root. Because for a square root, you cannot take like things that could be negative as an input. So by plus some small values right here, we are avoiding it to be taking negative input whenever we have a numerical unstability or rounding error things. So this is just a layer normalization. This xn, the n stands for normalization. So we are using a normalization right here. So what does it mean by layer normalization? The layer normalization has to have a learnable, a trainable weight and bias to replace the original, like the scale, which is the standard deviation right here, and the bias. So we have rescaled. This is the same dimension as the x minus mean. So we rescale the output and adds the learned bias right here. So this is a layer normalization. This normalization is done for each layer. Okay, so we got the layered normalization. It's pretty simple. Kind of like a batch normalization, but batch normalization is done over a batch, and the group normalization is done for each group of the in the layers. Okay, so this is layer normalization. And for a linear layer, it is then linear layer. We still got a W and B, but instead of you can see that it is a component element-wise multiplication, and this is a matrix multiplication. So instead of their dimensions are not the same, although they look pretty much the same. We got the W and the B, but this is kind of like a, if your output is xn is like a dimension 100 dimensional things, it will have the length of it is 100, then the length of the W is also 100. So you simply do the multiplication element wisely. Also, this is a faster and a smaller, quicker operation. But this is a matrix multiplication, like other linear layer. So I use this matrix multiplication operator in Python to do the same. Okay, so this is just a linear layer. You can see that xw plus b. Exactly the same as the mathematical notation, except in Python it uses a strange notation for like a matrix multiplication. It has been a long discuss about what kind of this notation should be, but so there are tons of discussion, which means this notation is not perfect. But by comparing other different options, they choose this one. Okay, so another layer we use is embedding, which we use for the token embedding, and we also use it for like positional embedding. We use the embedding here is it is just a lookup table. So the weight is simply a metric, and when we call this function, like x is like a number, like 1000, or a sequence of number. It could be a number or a sequence of number. But even if it is a sequence number, we can use the fancy indexing in NumPy. So it will return a sequence. But this is just a lookup table to check. Okay, suppose this is just a number, like 122. We simply find the 122th element in this metric. That's it. So embedding is nothing difficult. The message I want to deliver right here is that if you see that when you read the paper, you see those kind of construction building block. If you feel that they are actually kind of too simple, too easy, it might be partly true and partly false. And the true part is they are actually, when we do implementation, mostly we fairly faithfully following the mathematical formula. They are nothing but the mathematical formula. You can see here, or like the normalization, element-wise multiplication, and the element-wise addition, and like a matrix multiplication and element-wise addition. And for embedding, when we say that it is easy, it is actually easy just to look at a table. But another aspect is that you still need to consider about the numerical stability, especially when you have a division or like a square root. So that's the differences between the paper and the algorithm. So the actually implementation, because there are certain details like technical details you need to have actual caution. So that's the differences. But in the principle, in the algorithm wise, they are actually that simple. Also, we give it a name like linear embedding or like a layer normalization. It helps you to memorize things so that we don't need to discuss the rows in everything all together. Like, okay, the linear thing is something that trainable W and trainable B, and we get a linear, actually a fine transformation. A fine transformation is a linear transformation plus some bias. We don't need to say that thing that long. You just remember that it's a linear layer. And same thing for embedding. I think some of you may feel more friendly or familiar with linear, but kind of a little bit intimidate about the embedding. It's only because you are not familiar with it. But if you are intimidated and not trying to understand it, you are not going to be familiar with it. So the only difference between embedding and linear, if you feel them differently, the only difference is you're more familiar with linear layer than embedding. So if you are embedding, try to understand, try to be open-minded. It is just that simple. And it's the same thing for layer normalization. Although it arguably is slightly more complicated than the linear layer or embedding, it's not that difficult. It is not that complicated because this is simply a normalization. Very standard normalization way, plus something like rescalability, or like rescalable it and rebias it. Okay, so that's probably the simple building blocks. They are sort of easy. We are always doing is saying that, okay, make you to do a corresponding from the name to the actually mathematical formula, and to confirm that they are actually nothing but this simple mathematical formula. And for coding things, I'm wrapping it in a more uniform way so that you can use them in a same manner. But this uniform way is inspired by PyTorch, and PyTorch is probably inspired by Keras, and the Keras is inspired by Torch. So I'm taking idea from other other frameworks. So they are provable interface for building neural networks. They are provably to work for convenient for building neural networks. But I'm not using this for training. This is only for inference. So I skip tons of different things like backpropagation things, like backward in PyTorch. So it make it much easier to understand than PyTorch. Okay, so we are going to consider some nonlinearity. The first is they are using GELU. It is not like a ReLU or ELU. or other things like it is GL, it is spatial nonlinearity. It is defined as this guy, which is kind of strange, but you can see that it's a hyperbolic tangent and square, it is a constant, another constant, which is the square root of 2 divided by n beta pi. Probably not a good idea to compute it every time because it is a constant. I probably should compute it beforehand and use it, and probably sort of need to expand it to a more flat formulas. But anyway, the purpose of this is coded to explain what it does. So I'm writing it as is the mathematical formula. So although this formula is a little bit kind of difficult to understand, but the good thing is you don't need to understand it unless, I mean, I'm not trying to explain this. If you are interested in how this is derived, you can see the GLU, like a Gaussian error linear unit here. This is using like ERF, this guy, and this guy here. Anyway, it doesn't matter that much, and it's just a choice of the nonlinearity that have certain property. So it is actually itself is approximate. The true GLU, the Gaussian error linear unit, is using ERF. ERF is a non-elementary function, which is the accumulative distribution function of the normal distribution, which is a pretty difficult nonlinear, non-elementary function. So it can be approximated in this way. So all this strange formula, strange constant right here, is try to approximate it. Another approximation is using the sigmoid, but 1.702x. We probably can use this one. It's more easier to use this one because this one is simple. The reason I use this one is to follow the original implementation. I'm not actually following the original implementation. I'm following like the PyTorch one and my like a mini GPT one, which in turn they are following the original implementation. So this one is only an approximation of this guy, and this guy may have certain spectral foundation, but you don't need to worry too much about it. It's just a nonlinear function. Okay, so we implement it right here. It is GRU right here, Gaussian Gaussian error linear unit. So this is chosen by using in GPT. So that's why we use it. And also we have a somax. It is just simply the somax in popular implementation. The only thing we do here is to make it more numerical stable. The only trick we do is for each A, we minus the maxima of the A. This is because the reason that we can do that is because each A need to go through an exponential. If this one is too big, the largest one is too large, the exponential may be overall, because you know that exponential grows very fast. So if a large element of this A in this array is going to be very large, the exponential may be overflow. Even though it is not overflow, when you do addition, it might be overflow right there. So instead, we are kind of normalize them by minus the maxima of it. so we can make sure everything is scaled according to this so that the maximum one is going to be 0. Because we are feeding them to be exponential, this formula is equivalent to the original one. Or you can prove it by like dividing every element, including the denominator and denominators, by the maximum element. So you get the equivalent formula. So the only thing we do here is to making it to be more numerically stable. The simple trick that we do, very common trick. The rest of them are simply the softmax. Okay, we are having another utility function that is specified designed for the multi-head attention. This is important for the implementation, which we call two heads. The reason is that if you see here, in the multi-head attention, this V1 goes through a linear and a linear here and a linear here. This K goes through this linear and the linear here. This Q goes through this linear and the linear and the linear here. But since they are all linear, we only need one linear. I mean, you can run one linear multiplication and the second and third. But why not just using one linear multiplication? The code is shorter and it's probably more efficient. And after you get the output, you just simply split the output into different sections. Then you are getting some equivalent results. 好，所以这边的事情是说，你看这个图看起来就是我这个 V 经过第一次 linear、第二次 linear、第三次 linear、第四次 linear， 就经过好几个不同的 linear。但因为它 linear， 我干脆做一次，一个大的 linear， 然后把它切分成小的 output。So that's what these two heads do. When we get an output, a big output, we separate it into small section of the output, equivalent length, equal length of output. Then practically, effectively, they are similar to running multiple linear transformation. So this is a function to split a big output to separate chunks of output for each head. You can see that we simply reshape it. We have a large, huge factor right here. We reshape it to be like this guy. Okay, so this is our self-attention implementation. It's kind of long, but it is more efficient implementation because we are doing certain key value catch. The reason is that this is used for inference. This code is used for inference. So the usage of this model is we are going to feed the tokens one by one. So for the previous tokens we already have, we don't need to actually compute the embedding, like key values again, because in previous turns we already compute them. So if this is kind of incremental things, we can only use them, the value we computed before, to reduce the computation cost. Also, we have this guy right here. But if you don't consider like the incremental case or other things, then probably there's nothing need to be worried about. Okay, so it can be shorter. So these are all for the catchy things. So it is not that scary. Okay, so let's see what we need for these guys. So first we need attention. we call it C attention is because this is a name from the GP2 like the safe tensor weighted file. So we call it C ATTN for this attention. And we also have a C project, which is doing the projection. And unembedding is just to get the size of how many embeddings we are going to have. And number of heads, this is just getting the number of heads and the head dimension or dimension of each head. And the mask, what is a mask? It depends on, it is a triangular mask, which you will see later. So like we discussed before, each token can only see the tokens previous to it, before it. It cannot see future tokens or any tokens after it. But here, it is not so important because we are feeding it one by one, but we are keeping it to be more faithful to the original implementation. And we are adding something like key cache, and the v cache, so we can catch the previous things like here. So if we are getting the same, input, mostly the same input, but with a new additional token. If this is the case, then we can use the previous stored cache to reduce the computational cost. Okay, so for each attention operation, we are getting something here. I kind of writing down the shape of the input. It will be something like the batch size, the sequence length, and the dimensional of the embedding. The embedding is shared by like a positional and the token embedding. They are the same, but this is what we get as the input. The batch size, the sequence length, and the embedding here. So we run the linear map on the embedding to get the first thing called the Y here. So this is the first part to get the embedding, to do a linear transformation. And then we do this vector have the shape of the base size, sequence length, and an embedding times 3. The reason that we will have this times 3 is because we are preparing for the key, query, and value. So you can see that, okay, after this one, we are split this vector into 3 vectors like key, query, and value. So basically, this is things that should transform the input into key, value, and the query. So each one will have key, query, and value will have a base size, sequence length, and an embedding. And then we split them into multiple head things like KQV we use two heads. Depends on how many heads we have. We split this output into small part of it. So if, for example, if the M embedding is like 1024, and maybe we have 4 heads, then each head will share, will get a 256 share of its part of information in this or in the original vector. 好，所以你看到这边基本上前面很单纯的，就是我们进来的东西 base size 反正就是 batch， 我们一定要做 batch 的嘛。然后 sequence length 所以它有你的长度可以是任何长度嘛，就是看你的长度。然后你每一个那个 embedding 的那个大小，然后我们基本上就是直接把它经过第一个 linear transformation attention map 把它变成3倍。这边就已经得到 KQV 了。这 KQV 我们先把它分成 KQV， 然后再把它分成不同的 head。其实应该用 QKV 啦，但是我这边顺序有点不太对。 QKV 的那个 dimension 都一模一样。好，所以这边怎么分啊？图 head 基本上就是原本的话，如果是1024，然后你有4个 head 嘛，你其实就把它分成256、256、256，就只有这样子而已。好，所以我们这边就完全是这边 map 只是说我 KQV 都做同样的事情，然后得到它的东西。好，所以这边的话，单纯的只是 reshape 而已。本来它是1024，但是我们要 multi head，我们就把那个1024分成256、256、256、256这样子。Okay, then we will check whether or not we are in the incremental sense. If it is incremental, it will pass. So it is kind of a leaking implementation, leaking abstraction. But we are kind of trusting this is an incremental test. Suppose this is an incremental test. Our sequence length is equal to the incremental plus 1. That means we're not actually passing the whole sequence right here. When the case is incremental, we're only passing the new element here, right here, because we are passing the new tokens here. And we are assuming this new token to be only one token. We are incrementally one by one. 好，所以这个 incremental 其实是假设说，我们现在我这边如果是 incremental 里面设成是 true 或者设成1的情况，代表我进来这东西并不是所有的那个 sequence， 之前的 sequence 就是之前你就用之前你记下来的东西，我这边是记下来一个新的东西。我的 sequence 是记下来一个新的东西，然后呢，我真正的 k 我要把 so the real k is this the catched k plus a new key, and the real v is the old catched v plus the new v. So we catch the k and the v, key and the value. If it is not incremental, then we simply use the original key. I mean, if it is not incremental, the key and the value should be, and the key and value should be, the sequence length should be like a 100, 200, or like a multi length. It is a length more, probably more than one. We use it directly. But if it is in the incremental mode, we're assuming that we are using the things that we are already catched, and the x here is not the full x, it's just a new token, the additional token. Okay, so the sequence length should be the incremental plus 1. The incremental should be, and we should check the incremental things is in fact same to the length of the KV cache. But anyway, no matter whether it is incremental or not, if it is incremental, we are concatenating the cache with the new k and the new v. If it is not, we are using the kv directly. Anyway, we are setting the cache to be k and the cache to be v. If you are not considering the case of incremental, you can ignore this totally. You can see that, okay, KQV is just like what we say before. The base size, sequence length, things like that. For the multi-head case, the base size, sequence length, the number of heads is, suppose it is equal to 12. The head dimension is equal to like 64, something like this one. Okay, then you just ignore all these things, because whether or not it's incremental, after this point, after the line 123, they are equivalent. Okay, so then we are going to get the attention map. The attention map is the sense that before what we say here, eventually we are going to attention map is the product after the softmax. So this one is not the final attention map. This is the one of the step we wish to compute for attention map. We are using the Einstein notation to do that. So we're using the np dot Einstein summation. Although it is, I mean, in the formula here, it is something like this one, QKT. But the thing is, we have batch size. We have a batch size. We have a sequence length. It's getting a little bit complicated. So in order to do whatever we wish to have, we're using a more flexible, like the Einstein summation. And it is quite readable because you can see that the input is Q. The Q is, and also we have a multi-head, so it makes it more complicated. But you can see that BMHD means this is batch size, M is the sequence length, and H is the number of heads, like 12 heads, and D is the dimension, the head dimension. This is the Q. And for K, it is BMHN. I mean BNHD, where B is the base size, N is another sequence length. Because we are doing pair. I mean, like N squared. If a sequence length is N, we are doing this pairwise, like the multiplication, like 100 times 100, different kind of multiplications. I mean inner product. So they are using M and N. They are using different variables so that we can match every possible pair of M and N here. And H is the same, so they are not going to. They are doing it sequentially. They are not trying to find all combinations. But for MN, because they are using different variables, they are using different combinations. But all B, like all the B, H, and the D, they are all mostly kind of like a sequential things. And for MN, we are using all possible combinations. But you can see that although B here B are the same, H and the same D are the same here, but for the output, we'll have like a B, M, H, N. So we are considering all possible pair of M and N. And for each batch and each H, for each B and each H, the D is doing the reduction. Like what we do for the dot product, they're doing a summation. The summation is over D because there's no D right here. If you are putting D right here, it's kind of like you'll get a really large array. It's doing the like a multiplication for each pair of MN and for each BHD. But since there's no D here, D is doing a reduction. So eventually we are doing, effectively we are doing the dot product along the D dimension. Along a D dimension. And for the multiplication, and for each pair of MN. And the B and H are compared, are considered as batch. 好，所以这边就是 Einstein notation，其实它算是可读的啦，因为你可以看到我们这边的，你注意看，就是 M 跟 N 是不一样的，然后这边输出有 M 跟 N， 所以 MN 是任意选择的。那 B 和 H， 你看 B 和 H 这边都 B 和 H， 所以这 B 和 H 基本上当成是 batch， 因为它这边有，这边有，两边都有嘛，但是它是留下来，所以它当做 batch。那 MN 是一边有一边没有，然后这边两边都留下来，所以它是当成是，就所有的组合你都要考虑。好，那 D 是被消掉的 ，D 这边不见了，所以 D 是被消掉的东西，所以它就是它的加法是对 D 那边去加的，它的加法是对 D 那边去加的。好，对，所以基本上就是我们 B 和 H 是算是 batch， 然后 MN 的话，我们做的事情就是做那个 inner product， 做点击，做那个内积点击那件事情。然后每一组 M 和 N 我们就去做，然后 B 和 H 不用，B 和 H 不用配啦，不用什么第一个对啊，因为它两边都一样的数字嘛，所以它就是像一个 batch 一样。batch 你就是先把你在思考的时候先把 batch 先移开，因为它就是批次去做。好，所以 batch 的话就是留下来，然后 MN 的话你就是两做组合，所有可能性，你这边有100个，这边有100个，所以你总共有10000种组合。 那每一种组合你就去做内积。那内积的方向是沿着 D 去做，因为 D 是被消掉的方向。所以这个就是爱因斯坦的组法。So this is in fact the this formula like QT, QKT. It just we need to consider about the batch, about the multi-head, and the batch and the multi-head are all batches because multi-head is also works like a batch. And we need to consider all the Curie and the key pairs, all different combinations of QK combinations. So that's why the MN are in different variables so that we are consider different combinations. And the multiplication is done, I mean, the inner product is done along the axis of the D dimension, which is the, the same thing you can see right here. You have KT here, there's the DK dimension here. Okay, so that's is a true faithful implementation of what we see in the paper. And also you can see that we divide by the square root of the self head dimension because they are all the same, so we can divide it all together. The only reason that we use Einstein summation is that we have to consider multi-head and batch. If we don't need to do that, we can actually use the multiple, I mean, like the notation, like the at notation in here. We can use this notation as well and consider Q and K. But the thing is, at least we need to consider about the multi-head. So the easiest way to do that, I believe there are probably some already other like tensor product method to actually handle these things, but they are sort of kind of varies different, treat different in different like PyTorch, TensorFlow, or NumPy. They treat different. So the simplest way to do that is simply use the Einstein notation. It is efficient and more readable and not confused. Okay, so if it is not incremental, we will have to handle the mask. So how do we handle the mask? It's simple. If it is not in a mask, we are make it to be negative infinity. And if it is in a mask, we make it to be as the original value. So if it is not in a mask, it is outside the mask, we simply make it to be infinite, negative infinite. That's all. Then we apply the softmax to the attention map and got our result. So finally, we will have the things that in the multi-head attention here. We'll have a concave and a linear. So again, we use the Einstein notation here. No. So first we have to do the all right, let me put here. We do the final one. After we get the attention map, we have to do the weighted summation on the value. So this one might be a little bit easier and may not be needed to use the Einstein notation. However, like I said, Einstein notation, this is not a must, but this is our choice. It's nice to have. I think Einstein notation is nice to have because we have multiple heads here, H here, and the batch here. Though this is simply a weighted summation, so I'm still using Einstein notation to make it easier to understand. So the some of rules is that if it requires more than 3 dimensions, you probably if you are involved try doing something like tensor product or like anything like a matrix product, but for like a things that higher than 3 dimensional or maybe 3 dimensional things, then you probably want to use Einstein notation to make things more clear. Also, I'm using Einstein notation. You can see that okay, we still have a batch and um, M and N here. Um, but you can see that we have a batch BMHN, and this is BNHD, and our output is BMHD. So we keep the length of the we are keeping the length of the Q. You can see that M is the length of Q, right? Although we know that M and N are the same, but anyway, we are keeping the length of this Q here, and the output dimension is using the value. This is the value, right? This is the dimension of it, and we are treating the the N is using for the summation part. The N is the length of the key value pairs, the length of your KV, like you can see it as a KV dictionary or KV making or KV pairs. So we are doing the sum, weighted sum over this dimension. Also, you can see that it is cancelled out. So we and the B and the H are considered to be batch as well. So this is how we do the weighted sum. And after we get this weighted sum, we're going to reshape it because this is actually concate, the concate things. But since we already get everything all together, we simply do the reshape. So effectively, this is concate. And finally, we're doing a linear mapping. Recall that the C projection is also a linear mapping. Then we are done here. And we get the dimension that we need. So although it seems a little bit longer, like it consists like 35 lines, or no, like more like 26 lines. But it is not that hard because we are considering the incremental case from here to here, and we are considering we are giving a lot of comment to here. So it is more like 10 lines or 15 lines, and everything here you can see that the only obstacle might be the Einstein notation. But if you understand what Einstein notation is, it is in fact a tools for you to more familiar or to understand the algorithm easily. But anyway, most of the case, if there's Einstein notation, it involves something like matrix multiplication, like here, matrix multiplication, and the matrix multiplication here. Mostly the matrix multiplication, Einstein notation is corresponded to a matrix multiplication somewhere here. So if it is really too difficult for you to understand what the Einstein notation is, I hope this is not the case. But if this is the current situation, at least you know that Einstein notation is a common way to implement the matrix multiplication. Okay, so this one is the self-attention operator right here. So for the block itself, this block, mostly like, like this block, but without this guy. We only have the first one and the last one. This block is called a transformer block. This one is called a transformer block. So we should implement the transformer block right here. The transformer block, that's supposed to see a code here. It has attention and an MLP here. Maybe I should put this one. This is more complicated situation, so I put this side by side so that you can see everything. So LN1 is you can see the the encoder part because we don't have this guy. So because you cannot see the mask right here, so they are essentially the same. You can simply see the encoder part here. So we have a layer normalization one, LN1 here. This is layer normalization one. LN2 is the layer normalization two. And we also have a attention map, attention operator here. Okay, attention operator here. And we have a MLP, first MLP for fully connected layer, and another MLP right here. So what we do here is these two guys, we combine these two guys together. These are just two layers. Recall that we have a feed-forward network that is MLP right here, right? This is a two layer. This has two linear layer right here. So we call this first layer fully connect, and the second layer called projection. So you can see we combine these two guys together. So first is MLPC FC here. This one is a linear layer, and followed by nonlinearity GLU, then followed by another linear layer. So the whole thing can be considered as one MLP. So MLPF is the feed-forward network. This one is the feed-forward network. Okay. By the actually compose, so we got LN1, L2, LN2 attention, and MLPF. These two guys are combined. We do a composition to make MLPF. So don't need to worry too much about it. So only need to worry about LN1, LN2 attention, and MLPF. So first, we do the LN1. This LN1 is actually this guy because they are stacked side by side, one by one. So in fact, we'll consider this LN1 before everything else. Apply this first. Then we apply the attention map. So there are small difference. You can feel these things at here. They do the layer normalization first instead of like at the end. You can. This is slightly difference between this illustration and this one. So we do the normal layer normalization first, and we do the attention. We do the attention. So effectively, it can feel like the layer normalization from the last block, but they are slightly different. You can see that we do the layer normalization first, then we do the attention. The difference is because we are doing X plus here. So this X is something that the X before we are applying it to the layer normalization. So we apply layer normalization to X and attention together, and add it back to the original X to get a new X here. So it can be seen as the output right here. Then we do the layer normalization 2 right here and apply the feed-forward network and add it back to the X. So it is arguably that the order of the layer normalization is kind of a change. But here it doesn't really specify the order of add normalization. So it can be still feel like the layer normalization is done after. It's done after the things. But I mean, it is easier to understand. Okay, the GPT is done some modification to this guy because it put the layer normalization first. Also, this is a slight variation of the things. Okay, so that's the attention block. The last thing we need to explain is the GPT itself. So how does the GPT? So we don't need the paper because this is for a GPT. We don't need a transformers paper. It is kind of independent to the transformer paper, orthogonal to the transformer paper. This is how GPT use this transformer block. We have all the building block. So first we have a token embedder. So this is embedding. We have a token embedder. We get a dimension right here from the weights, and the because it is trend already trend, so we get the weights right here, and also we got a positional embedding, which is also read from the safe tensor file. It is pre-trained. So this is a token embedder. This is a positional embedding, and the context lens we know that because we have so much positional embeddings available in this way. So the maximum context length is the size of the lookup table for the positional embedding. And the mask, we're using a triangular mask all the way through all the operation. So although there is option for a mask, but we are using the mask that is a triangular one because this is the triangular one is used for like the things that you can only see the things before you and not the things after you. So there is a diagonal below things to be 1 and above things to be 0. So this is a triangular one. We use NP-TRIL. This is a triangular, lower triangular things to do, to do to control the triangular metric. Okay, so this is the actually means how many transformer blocks it has. And for each transformer block, we're using the same head and the same mask all the way. So this is all the blocks, we put it in a list. And finally, we're getting LN if the final layer normalization. This was the final layer normalization. And I'll get in the head size right here. The how many heads? So we can give LM heads. Okay. This is not. This is the final one that we need to actually do. This is corresponded to the this part. This is how we actually compute the probability for decoder in GPT. In GPT, how we actually compute the softmax, the method we compute softmax in GPT. Okay, so let's go back to the code. You can see that this is called the LM head, which is actually just the embedding, the token embedding itself. I will explain it a little bit later. But this it has a different name. It has an option to be another a separate matrix other than the token embedding. But it is very common, and in GPT2 it is the same as the token embedding lookup table. But certainly you have an option to change this one to another metric. We'll talk about it later. So here is the whole process of the GPT2 works. Here first, you got this sequence here. We are handling whether or not it is incremental. If it is incremental, we do certain things. If it is not, we'll do certain things. So suppose it is incremental. It is not incremental. Actually, we're doing things like the positional encoding. You can see that we can do the positional encoding to using the positional encoding lookup table. So simply look up these guys and get this output. So get the positional encoding. So the first n we get the first n. But if it is just single token, we find the position right here. And we use the token embedder to find the token. And this is token embedding. And plus the positional embedding right here. We can simply call the WDE, but I'm operating on I mean the original version, because we are not considering a KV cache. We are considering more simple case. We can simply call the embedding like what we are planning to do, like call here to find this guy. But instead, because we are considering more, this is a leaking abstraction for sure. This is not the ideal way to do that. But the purpose for you is to understand what it does in the actual algorithm. So you can see that we actually find the last token embedding right here by using this way. This one is a last token. So this is a number. So we use this number to find out the corresponding embedding for this token. And we simply add them to the positional encoding. So this is our X. We simply find this X. But if this is not in the incremental mode, we'll have to compute everything all together with the mask, of course. So we compute the positional encoding all the way, and we can simply call the WPE itself and plus the positional encoding to do it all at once. So this is the original way. But to consider the incremental case, we do things like this one. Okay, so we make it to be has a batch size 1 because our implementation consider batch size. But for the GPT itself, we are mostly work on a single batch size of 1 and without a batch. So to make it like a batch which has a batch size 1, we consider new axis, the batch axis, and put everything else as is. Then we apply to, okay, after we get this X is already got the token embedding plus the positional embedding. Then we apply this X to each of the block. You can see that's pretty simple. This X is equal to block X and run through these loops through all the blocks. And finally, we got the last layer normalization layer here. And then we simply do a metric multiplication for this X to the LLM head. So basically, recall that in our case, this LLM head is simply the token embeddings. So we have tokens like you can imagine like this is a token 1 embedding. 1, 2, token 2. Of course, we start from 0. It's because this is NumPy is Python. 3. Okay, so our output X is a sequence of things. This is X. It's a sequence of things. I mean, it is output right here. We simply, I mean, X is is a vector. So we simply do the multiplication, I mean, the inner product of this X to this guy, and to this guy, to this guy, to this guy. So basically, we are finding the similarity of our output X to each of the token. So consider in the incremental mode, we are consider the next one. So even if it is not in the incremental mode, we are not too worried too much about the previous output because we are only need to output the next one. So I only need to consider this X is just a factor. Although our output may be a sequence, but we're only interested in the last one. So for this last one, how do we determine this is just a vector that has the same size of the, like the dimension, the same dimension of the embedding. But how do we actually determine this X to the next token? We simply walk through all these tokens, embeddings, the 0, 1, 2, 3, to find the most similar one. But we're not doing a hard max, we're doing a soft max. So we simply do the multiplication, not doing the inner product to this one, to this guy, to this guy, and get the similarity, right? How similar it is. And this, by applying this to the softmax, we can get the probability. Okay, so the last factor is represent a factor, and if it is exactly like the one of the token, then it's kind of like a hard max, like a dictionary match. But we are trying to use a soft dictionary, kind of like using a soft dictionary, like we say, like in attention. So it's sort of like an attention. But this one, we directly use the embedding lookup table to see the most similar embedding as our output and to construct a probability. Okay, so that's the output. We're outputting the last one only. You can see that although it works for the whole sequence, we're only outputting the last one. Okay, so that's all for the GPT algorithm. So in the practice, you can see that, okay, here we already load one of the, you have to use the curve to download the safe tensor files. And you can see that we read the weight here and construct our GPT class right here. And this GPT can be already used to generate text. So for encoder here, we use a tick token encoder to encode in a GPT way to do the encoding. And here is a loop for generate all the GPT tokens. So the output of this one is the logit of the next token. And it will have the size of the whole embedding. So a typical way to do that, to do the sampling, is to using a temperature. But if you are not, we'll talk about temperature a little bit later. But if you are not considering the temperature, you are just this is just a logit. You can totally ignore the temperature altogether and feed it to the softmax and get the probability right here. We're also using a top K, which we are also discuss it a bit later for a reason. But the top K is simply the temperature is used to manipulate the probability. So the lower temperature, it will go into more make the output less random. The higher temperature will make it more random. So if the temperature is 1, then we are using the original logit output. But lower temperature, it will be more stable to be less random. And then your higher temperature, it will be more random. And we are using top K selection method to only consider the top K. The top K is predefined. We are defining the 15. So for next token, we are only consider the top 50 most likely tokens to our candidate as our candidate. We are also considering using like a top P things. So if a probability is, no, we are not considering. We are only, our threshold is dependent on the top K. So Well, consider only a top K, and according to the to adjust its probability to generate the next output, and append it to a X, and run this loop again. Also, this is the whole loop for generate new text. Okay. We take a while to actually explain how the GPT or the GPT-like model works. So let me give you a quick review of language models and what it is. So this is taken from the mini course from last semester. We're going to, in the next semester, this mini course, like language model mini course, is going to discontinued because I think most of the content I will cover in the generative AI, and we'll change the course to another one. But anyway, this is the slides from the last semester, and for the Stanford CS 224, this is a course provided at Stanford Computer Science, which is a pretty good resource that you can find materials. If you are more from, like I said, there are different learning patterns. If you are more familiar with learning things more systematically, or you prefer to a more system way to review the previous work, then this one is one of the good resources that you can do that. So first, we mentioned it a little bit before, like in homework, what is a character or word or token level things. So let me give you a walkthrough about why we need to do that. For a character level, we have already tried it in the homework, or like in the we explained before, that like an n-gram things. Although you can, you are not limited to n-gram model. You can use like LSTM or like in the GPT-2 to apply to the character level. But the thing is, character level is a little bit still a little bit too difficult problem, because although it is still has a very good result, but I think because language problem is a very difficult problem, so character level induce some difficulty. So that's why people does not choose. I mean, the popular model are using token level, not instead of a character level. That's the reason. But I still, if we have a better model, better data, probably people will switch back to the character level instead of token level things, because there are still some issues with token level. But currently, it seems like the best recipes so far for current technologies. But character levels works. It is a choice. We didn't choose that because language model is difficult. So the current formula is split it three part of the problem into tokenization, and the part of the problem into like a language model. Okay, so there is a homework in the last semester to run the tokenized level things on your data. But this is not a homework in this semester, in this class. Okay, another way is to use a word level things. It's quite kind of apparent. So if everything in the, but it the things it is not in the dictionary, we simply use a noun instead. It seems that if a word is not in a dictionary, maybe people does not use it very often, so it may not be a huge problem. Back in like 10 or 15 years ago, when people are doing natural language processing, probably is one of the way to do that, because we have a dictionary. It is good enough, and you may heard something like word two factor, which is popular. So that is one popular approach, at least in certain scenario. It kind of similar. It kind of have a similar idea to the tokenization level, because it separates a difficult problem into two parts. Like you train a word two factor model first for word level handling, and you use this factor like in a LSTM machine or like a GI, like an RNN machine to handle the other part of the thing. It just they separate in different way. So that is also a valid approach. But what's the drawback of word level? Let's consider this example. The first, if this sentence contains only the common words, then it is fine. Like I like to eat apples and bananas. Oh, by the way, this slide is perhaps comes from one version of the sample class. So I have no credit. I take no credit about this slide. And maybe a few of the following slides. Okay, so if everything is common word, then it works fine. But sometimes it has a real word. So maybe your dictionary is not big enough to contain this real word. So in this case, these things are going to be unknown. And sometimes people, even though you can see, okay, the thing is kind of like twofold. If a word is not too rare to happen, it is frequently seen enough, then probably it should be put in dictionary. If it is not in the dictionary, it should be so rare, so infrequently used, so it is not going to affect the real performance of our model. So I mean, after all, even if you are a person, you're human. You are human. I mean, we are human. When we consider like this word that we never encountered before, we probably have to use the context to guess its meaning. This word is as good as like you're unknown to us. Although you probably can use some like okay, PER maybe means something, or this is S means multiple things. It might be something like a noun or something, but that might not be so useful. So it might not be that bad. I think this is a valid argument, but the thing's going to be more difficult than this kind of imagination or this setting, since because people tends to misspelling things intentionally or unintentionally, like LVOE. So this still doable that you collect common misspellings, but it is already going to be too huge to collect. So arguably, you can still collect all the kind of misspelling, and there are also kind of alternative spelling like TXT and FRNDs. And unlike although they are still arguably, you can still collect a huge dictionary containing all the misspelling and all the alternative spelling. But the difference between the real words and the alternative spelling and the misspelling is that we can actually understand what it is. Like TXT, we know it's a text. FRND is a friend. And the LVOE, we can kind of have a guess that it is a misspelling. Unlike the case for real words, we have no hope to knowing what it means unless we're doing some context and guessing. And also there are some newly invented words like crypto mining. And a lot of cases, although it is mostly in another scenario, it is a composition of words. So it is going to be kind of like the misspelling of alternative spelling. Although it is not in the dictionary, you kind of have some idea of what it means. And besides, there are more language than English. Like some language like Japanese, it has a group called agglutinative language, like combine like the ototo, like young brother, is a combination of like the younger and the person. And some language contains extensive compound words, like in Germany, this is a valid word. And some language like Japanese and Chinese, um, it doesn't even have a clear separation of a word. So when we use the natural language process before, like 10 years ago, people are using like a Jeba or something to do the cutting the word first. There are a lot of different consideration. So that's why people doesn't use the word approach. Okay, so then that's why people using a thing that can automatically generate a dictionary. And this dictionary is not specifically explicit for the word that we know. It is sort of like a subword level. It is not a character. It is too inefficient. It is not a word because it cannot be so complete. So we are choosing something in between using some kind of algorithm. Okay, so one popular method is called the BPE, the byte pair encoding. So how it works, it starts with the most basic form of a text. So it's kind of like a bottom-up approach. We try to build a dictionary that can combine every possible word. So the idea is, even though it is a totally new word, it can fall back to the character level. Like LVOE, we can actually tokenize it into a LVOE, something like that. So we have a small dictionary. Start with a small dictionary. Okay. So like every byte or every thing. Then we use an algorithm to add new tokens. Like the most frequently, we still have a training data. So we consider all the combination of the every two things in the dictionary. And if it appears a lot in the dictionary, in the training data, we put it into the dictionary. We add them into a dictionary and doing it one by one. Or we have a size limit like 50,000, or maybe you will have a huge dictionary like 100,000. When we reach the limit of our predefined size of the dictionary, we stop right there. So we have a pretty comprehensive dictionary. But this dictionary still contains some like fundamental symbols, like character, letters, everything. So even in a worst case, it can still fall back to the character level. Also, that's the BPE and tokenized works. But this this is an example like if our training data is like a HUG happens 10 times, PUG happens 10 times, 12 PUN happen 12 times, and this so on. So first, our dictionary, it starts with like our beginning at the beginning our dictionary like HUGPN. This is our dictionary, and then we do edit it one by one. So at the beginning they are separated into a character, and after this one we find that the UG happens a lot. So the UG becomes a new items in the dictionary, becomes a new token. So we processing the data again. So we have H and the UG, P and the UG, and the P, U, N, P, U, N, and H, U, G, S. And we find like the UN is very common. So we add the UN into this dictionary and do it again. until we reach the limit or the size of the dictionary. But it is not the only way that people use for tokenization. There are instead of using BP, people may use word piece. It's kind of like a BP, but it has a different definition of what is most frequently. BP uses the absolute frequency. But you can see that each character, each token in addition may have a different frequency. Sometimes if two low frequency tokens always connect to each other, although, the absolute frequency is low because these two tokens have low probability. But we probably should put this combination into our dictionary because if consider another two popular tokens like in English, like maybe like A or T or like E or like N, because they are used a lot in English diction, in English text. So even if they are not entirely correlated to each other, just by probability, they probably are next to each other in a lot of different times. So we should consider, we should take this situation in consideration. Also, by using a different way to interpret which one is the most frequently used, we can construct another algorithm called the word piece to choose different, use a different way to choose new tokens for adding into the, for extending our dictionary. And they are also using a unigram model since combined with the sentence piece. Like unigram is more like a top, like we start from a large dictionary and shrink it. It more like a top down and the bottom up difference between top down and the bottom up approach. So use a unigram and sentence piece. This is probably one of the popular combination of ways to do tokenizer. So I'm not going to too detail in this method, but I'm just giving you an impression that there are different ways to using algorithm to determine the token, the tokens that we should use by a certain training data. So the tokens are dependent or biased by your training data. So in early language models, usually the reason that they didn't perform really well in traditional Chinese is mostly because the tokenizer didn't consider the traditional Chinese. The tokenized didn't train on traditional Chinese text. So the tokenizer is more like a character base if you are handling traditional Chinese text. So even if you do the fine tuning on the popular large language model, they will still have a certain unsatisfying performance on the fine-tuned models. But newer models mostly consider about the multi-language. So chances are their tokenizer is getting better. So one thing you need to look up at is a tokenizer table. If you want to try to fine-tune a model, make sure the tokenize is okay, because that is a simple part. That is something you can manipulate easily. If you feel that some tokens that is very frequently used in your scenario, in your use case, but it is not in the token table, in the token list, you probably should add new tokens and retrain, refine before you're fine tuning the model. Okay, so back then people are train the word embedding first, then use like word to vector. Even though there are difference between word and token, but similar way you can train the token to vector in a similar manner. But currently the pre-train is usually using a more like a self-supervising way, kind of like word to vector, and by reconstructing the sentence. So they are not trying to do the train the embedding and like a transformer separately. They are training them together. So that's the a difference. If you are familiar with the word to vector like model. Okay. Okay, so we are run out of time. So next time uh, we are going through the training method about like BERT. Although it is not BERT like T5, like encoder, encoder, decoder, really quick. But although they are not generative model, but they are kind of useful to understand or to learn what it is. We are focusing on the decoder case, which is not much because it is still autoregressive. And we are going to cover the scaling rule because they are interesting. So next week, we're going to talk about the training things, about the language model, and discuss certain architecture, like the mixture of experts, like rotatory positional encoding that is popular in modern architecture. And we'll discuss the details about like llama, how llama is, what is llama, and what it, like the linear, like a nonlinear function, and the transformer variation is used, like DeepSeek, like it's KV cache, not KV, like a KV compression. Oh, I forgot the name, like, but and its own mixture of experts variation. Also, we're going to talk about these things in next week.